Hi friends and students. This is part 2 of the lecture series on test questions in nuclear physics. The emphasis in this particular video is analyzing questions involving radioactive decay rates. Before we start answering questions, we will first review some terms or concepts related to nuclear transmutation or the rate of nuclear decay. First in the list is the meaning of half-life. So half-life refers to the time it takes for one half of the radioactive nuclei to decay or transmute. Okay, what does that mean? Let's look at this graph. The graph of the time t across or along the x-axis versus the number of radioactive nuclei indicated by capital letter N. So at zero time, we say that the number of nuclei of the original number of nuclei, the substance, is labeled N naught. So that is at time equals 0. So after a time equivalent to the half-life of this particular radioactive element, you will notice that one half of the original number of nuclei has already disintegrated or has decayed or transmute. Then, after another half-life, for a total of 2 half-lives, there is again a decrease in the number of nuclei remaining. So we now have 1/4 of the original number of nuclei remaining. Remaining, in other words, still in the form of the original nuclei, and that 3/4 have already transmuted or have been changed to an entirely different element. Okay, so if there is again another half-life for a total of 3 half-lives, you will notice that the number of nuclei remaining has again decreased by half. All right, so it now only has 1/8 of the original number of nuclei. All right, that means 7/8 of the original nuclei have already undergone nuclear transformations. So the process goes on, and if you're going to plot the points corresponding to each number of radioactive nuclei remaining and for every half-life, you will come up with this curve sloping downward to the right. Okay, we say therefore that the half-life, as shown in this particular graph line, is somewhat exponential, right? So, to further understand how half-life is related to other terms or concepts, our formula, mathematical formula, for determining the half-life is equal to, okay, half-life labeled T sub 1 half is just equal to the natural log of 2 divided by a constant, lambda, where lambda is what we call the decay constant of a given radioactive isotope. So using your calculator, the natural log of 2 is equal to a value 0.693. So half-life, in short, is just equal to 0.693 divided by the decay constant for that particular radioactive isotope. If it is the decay constant that you're looking for, then we'll just transpose the equation and we will get the formula for lambda, which is equal to the natural log of 2 divided by the half-life of this isotope. In short, lambda, or the decay constant lambda, is equal to 0.693 divided by the half-life. Now, negative dn quantity T over dt is what we call the rate of the activity, all right? How fast the transmutation or the transformation take place. So that means we are talking about the change in the number of nuclei that undergoes nuclear transformation as a function of time. Okay, so the rate of nuclear decay, therefore, is just equal to the product of lambda, that means it is a constant, multiplied by the number of nuclei remaining, okay, and of course the time t. So from this, it is clear that the rate of nuclear decay is directly proportional to the number of nuclei for a given time. That means the more nuclei there are initially, okay, the longer is the rate of nuclear decay, right? And also, for a given number of nuclei, the longer the time, that means the longer is the rate of decay. In other words, it takes longer time, no, for the particular isotope to undergo nuclear transformation. Now, another important formula is if you're trying to determine the number of nuclei of a particular radioactive element or isotope, okay, after a given time t, how do you determine the number of remaining nuclei that has not yet decayed? So it is just equal to the original number of nuclei, that is n naught. Capital N is the remaining after a given time t. All right. So to get that, we just multiply the original number of nuclei n naught multiplied by the value of the Euler's number denoted by small letter e to the power negative lambda t. Take note, the negative lambda t is the exponent or the power of the Euler's number e, whose number or value is equal to 2.718. In other words, when you are determining the number of nuclei remaining, you just first find the value of Euler's number raised to the negative lambda t, assuming you know already the value of the decay constant, and at a given time t, okay, you can determine the value of this term e, Euler's number e, raised to the negative lambda t, okay, and then multiply it by the number of uh, the original number of the nuclei, okay, m naught. So you'll be able to find, you know, the number of nuclei remaining after that time t. Also related to this is when you want to determine the activity, all right, the activity labeled as capital A. Okay, when you say activity, we are referring to the reciprocal of the number of nuclei that is disintegrating or that is decaying or transmuting. Its unit in the SI system is the becquerel. So if you want to know the equivalent becquerel after a time t, you just use the same or similar equation. You just multiply the original activity A naught multiplied by the value of Euler's number raised to the negative lambda t. So these two equations are somewhat similar. Here we have the definition for each symbol that we use in those formulas or equations. Okay? There is a negative sign in the rate of nuclear transformation because, as shown in the graph, as time passes, okay, we notice that there is a decreasing. There is an exponential decrease in the number of nuclei that is remaining after any given time t. Hence, the negative sign is emphasized in this formula. Okay? But if you are determining exactly what the rate is, and you just multiply the lambda times the number of nuclei remaining, and then multiply by the time t. You just discard the negative sign. Alright? So, we will be using these formulas in the next set of questions that I have selected. For now, let's also take note that the SI unit for activity, that is represented by capital A, the SI unit is what we call the becquerel, whose value is exactly equal to 1 decay per second. But if you're going to define it in the context of the number of nuclei, capital N, remaining after a given time t, we can also say that 1 becquerel is just equal to 1 nucleus divided by a unit time second. There is an older unit known as the Curie in honor of Madame Curie, all right, who discovered one of the radioactive elements she discovered, of course, is radium, the isotope radium 226. All right, so it can be shown that 1 Curie, symbol for Curie is capital C I, and that is equal to 3.70 raised to the 10th power becquerel. In other words, 1 Curie is a large value of nuclear activity or radioactivity compared to 1 becquerel. So, for 1 becquerel, we say that there is an equivalent of 3.7 raised to the negative 10 Curie. Alright, so we will now start answering some prepared questions. Question number 1, letter A. A radioactive element has a half-life of 2 days. If you start with 20 grams, how much would you have left after 6 days? Question 1b. 64 grams of a radioactive isotope decays to 4 grams in 6 days. What is its half-life? And question 1 does C. A radioactive nuclide has a half-life of 20 minutes. How long will it take 30 grams to decay to 4.5 grams? So these three questions will just actually apply the concept of half-lives without necessarily using those formulas that we introduced earlier. So this is just somewhat like conceptual questions. Let's begin with letter A. Right. So uh, if you're going to analyze, okay, uh, the given question and the data, we can see that in 6 days, okay, there will be 3 half-lives because the half-life for this element is said to be 2 days. So 3 half-lives, okay, 3 half-life corresponds to 6 days. All right. So after 6 days, the element has already decayed by 20 grams divided by 2. All right. And that will only give 10 grams. That is after one half-life. All right. After another half-life, okay, for a total of 2 half-lives, these 10 grams will again decrease by half. That means 10 grams over 2, we will get 5 grams remaining. So what we need are 3 half-lives. So still, after another half-life, okay, that 5 grams will again divide by 2, and we will get as our answer equivalent to 2.5 grams of the substance remaining. 2.5 grams. This happens after 3 half-lives have passed. So that is our answer to letter A, 2.5 grams. Next question, letter B. All right. In question letter B, if you're going to analyze the given, it takes 4 half-lives. Okay, 4 half-lives for 64 grams to decrease to 4 grams. Okay, you can just keep on dividing 64 grams by half until you reach 4 grams. So 64 divided by 2, that's after 1/2. That is after 1 half-life. 64 by 2 is 32. Then, after another half-life, 32 divided by 2 is 16. Alright? 16 grams, but that is after 2 half-lives. And then, for another half-life, 16 divided by 2 is 8. So that's after 3 half-lives. And finally, after another half-life, we now have 8 grams divided by 2. That is, we get 4 grams. So, that means you are going to divide the given days of 6 days by 4. Alright? You're going to divide 6 by 4 because there were 4 times that you divided the original value, the original mass, to be able to get 4 grams. Okay, 64 grams has to be divided by 2. Okay, how many times? You are going to divide 64 grams by 2 in 4 times. That means the half-life, which is just equal to 6 days divided by 4, that's how we got 1.5 days as our answer to letter B. And finally, for letter C, all right, for letter C, it takes, analyzing the question, it takes 3 half-lives for 36 grams to decrease to 4.5 grams. So just like in letter B, you can do it by counting. Okay, divide 36 grams by 2. All right. By the time you reach 4.5 grams, okay, 3 half-lives have already passed. Okay, 36 divided by 2 is 18. So that's after one half-life. All right, or 18, I should say, 18 grams. Then 18 grams divided by 2, we get 9 grams. Then 9 grams divided by 2, we get 4 grams. So we actually use 3 half-lives. 3 half-lives in order to change 36 grams to 4.5 grams. So what will you do with that? You are now going to multiply the given time, all right, the given time, which is the uh, half-life of this nuclide, 20 minutes. So after 3 half-lives, that means at our answer, the total time will be 60 minutes. Because the question is, how long will it take 36 grams to decay to 4.5 grams, given that its half-life is 20 minutes? So our answer is 60 minutes. Right? So these are simple questions pertaining to the concept of half-life without requiring us to use the mathematical equations. Question number 2. Suppose there are 3.0 raised to the 7th power radon atoms whose half-life is equal to 3.83 days, or when changed to seconds, that is 3.31 raised to the 5th power seconds. Alright, so these radon atoms are trapped in the basement of a house. Question letter A, how many radon atoms remain after 31 days? Find the activity, okay, for letter B question, find the activity just after the basement is sealed against further entry of radon. And letter C, find the activity of radon 31 days later. So, before we proceed to our solution, may I just uh, give some what we call trivia information about radon. Radon, uh, as we probably know, is the one of the byproducts or a daughter nucleus when radium 226, okay, radium 226 emits an alpha particle, okay, the resulting daughter nucleus is radon 222. All right. Radium 226, these are found in rocks and minerals, okay, below the ground. So it's possible that uh, some houses are built on top of these rocks and minerals, which have radioactive radium contained in those rocks. And if these rocks, if this radium, all right, elements, radioactive elements, emit alpha, it's possible for radon gas to be emitted. All right. So unlike all other elements in the nuclear decay series, all right, radon is quite unique because it is in gaseous form. All right. Another thing, radon is denser than air. So what happened is, if radon gas is able to uh, what do you call pass through, okay, the crevices, the small openings in your basement, it's possible for radon gas to accumulate. All right, to accumulate in your basement. They don't rise into the atmosphere because they are denser than air. All right, and the problem about radon, uh, as we will see in this problem, okay, it's also radioactive. All right, radon by itself is also radioactive, so it can emit what you call radioactive particles such as alpha, which can be uh, dangerous when uh, inhaled by a human or by a person. All right, so going back to this problem now, okay, our first question, letter A, okay, we are asked to find the number of radon atoms that remain after 31 days. That means after 1 month. So the first thing that we have to find is the decay constant lambda. Using our formula earlier shown, it is equal to 0.693, that's a constant, divided by the half-life. All right, the half-life of radon is already expressed in, or let's use the original half-life in days, which is 3.83 days. Right? So dividing 0.693 by 3.83, you will get this value for lambda, equivalent to 0.181, all right, per day. This means that the decay constant for radon is 0.181, all right. Radon nuclei disintegrates per day, all right. 0.181 disintegrations of radionuclei occur in one day. That is the meaning of the decay constant lambda. All right. All right. So after knowing the lambda, we will now find the number capital N of radon atoms remaining after 31 days. Using that formula, capital N is equal to N naught, okay, multiplied by the Euler's number raised to the lambda t power. All right. So we just substitute uh, the given what do you call this? The given number of nuclei at time 0 is 3.0 raised to the 7 nuclei. That's n naught multiplied by the value 2.718 raised to lambda times t. All right? Since our decay constant is expressed in reciprocal day, so our time t should also be in days. That is 31 days. So we notice that the unit day cancels out, leaving this number 2.718 with a power that is unitless. All right? It is unitless. And using your scientific calculator, where you can find there the process of determining the value of the Euler's number raised to a given power, such as negative 5.611. All right? So after getting the value, this, you will now multiply that to n naught. And our answer will come out to be 1.1 times 10 to the pip. What is the unit? This now represents the number of atoms of radon, or the number of radon nuclei. All right? The question specifically mentions the term atoms. So radon atoms. How many radon atoms? But that can actually be interpreted also to mean radon nuclei. Right? So that answers letter A. Letter B. How do you find the activity? All right. The activity express lambda in reciprocal seconds. That's the first thing that we will do to be able to find the activity. Again, we need to express the decay constant lambda, because what we got earlier was in terms of the reciprocal day. What we want is expressed in reciprocal seconds. So all we need to do is change, okay, get the equivalent of uh, 1 day, how many seconds. That gives us this value for uh, lambda 0.693, divided again by uh, what we call equivalent, the equivalent half-life, but this time expressed already in reciprocal, all right, second. All right, so our final answer for lambda, already in reciprocal second, is 2.09 to three significant figures, 2.09 raised to the negative 6 per second. Okay? So, we now proceed in finding the activity A, capital A. But, in terms of the number of decays, okay, we first try to determine the activity using the formula decay rate. All right, our decay rate delta n over delta t is similar to what we mentioned earlier. All right, the negative of the derivative of n as a function of time. That's why there's over dt, and that can be expressed also as delta n over delta t, and the negative sign is now placed, okay, in the term lambda and naught. All right, and if you substitute, okay, there is a negative before the parentheses, 2.09 raised to the negative 6 per second. This is our decay constant expressed in reciprocal second, and then multiplied that by the original number of nuclei, which actually is given 3.0 raised to the 7th nuclei. Okay, but there is no need to put the word nuclei anymore, all right, because that's understood to be the number of nuclei, okay, that is remaining, all right, that is remaining. All right, so using your calculator, we will get this value, negative 63 decays per second. This is now the number of decays per second, or the rate of nuclear decay, equivalent to 63 becquerel. Okay, becquerel can also be can also mean the number of decays per second. All right. So this is our answer to letter B. All right. In other words, at zero time, when the radon atoms, the leakage from the underground, all right, has been sealed, all right, whatever crevices or openings you have in your basement have been sealed so that further entry of radon gas is stopped. So at that very moment when the basement has been properly sealed from further entry of radon, that is where our time started, at time zero. But that particular time, there is already an activity amounting to 63 becquerels. All right, that is the meaning of the question in letter B. All right, and 31 days later, what would be the new activity in the area? So we expect that the number of activity will decrease, okay, from 63 becquerel to a lower value, because activity in a way is giving us the idea of the number of nuclei decay, the number of nuclei remaining after 31 days. How many more nuclei of radon are there in the area that still continuously emit radioactive particles? All right. So our answer to letter C is, we now use the formula, exactly the same formula, but we will now use our value for n that we got earlier in letter A. All right. What we got in letter A is capital N is equal to 1.1 raised to the fifth nuclei of radon. So that's what we are going to use here. Multiply it by the given, what we call decay constant. The decay constant expressed in reciprocal second. Okay, because this number of nuclei understood to be the number of nuclei remaining after 31 days. As you will notice in our computation in letter A, when we computed capital N, that is the number of nuclei of radon remaining after 31 days. So the result, if we do our math, we will get this delta N over delta T amounting to negative 0.23 decays per second, or just omit the negative sign and we can use becquerel as our unit for activity. So as earlier predicted, after 31 days, the activity has already decreased from its original 63 becquerel activity. It's now down to 0.23 becquerel. Question number 3. The radioactivity due to carbon-14 measured in a piece of a wooden casket from an ancient burial site was found to produce 20 counts per minute from a given sample, whereas the amount of carbon from a piece of living wood produced 160 counts per minute. The half-life of carbon-14, which is a beta emitter, is 5,730 years. Question is, what is the estimated age of this artifact? All right, the key concept that we will apply here is to find the age of a sample using radioactive dating. Okay, we have to measure its present activity and then determine what its activity would be or would have been when it was formed. The age is proportional to the logarithm of the ratio of these two activities. So our solution, we indicate that the activity at time 0 is, all right, 160 counts per minute. That is our A naught. And what do you call, the new activity, okay, has been noted to be 20 counts per minute. After a given time has elapsed, all right, the new activity is noted as 20 counts per minute, which is, of course, much lower than the original activity, 160 down to 20 counts per minute. So, okay, given the half-life of the element or carbon 14 isotope, which is 5,730 years, okay, we convert it to its equivalent in seconds. Right? So, using the equivalent factor in 1 year, there are 3.16 raised to the 7th second. So we will get as our half-life for this isotope carbon-14 is equal to 1.81 raised to the 11th seconds. That's the half-life of carbon-14. We can now therefore find the decay constant, all right, using the formula lambda equals 0.693 divided by the half-life in seconds. So our value for the decay constant lambda is equal to 3.83 raised to the negative 12 per second. Right? So our lambda is expressed in reciprocal second. We will use the relationship between activity initial A naught and the new activity capital A using this formula. Okay? A is equal to A naught multiplied by Euler's number raised to the negative lambda t power. Since we already know lambda, we can substitute, uh, but first transpose the equation so that we can find the value of the time t. Okay, so uh, from this formula, we can have the equation to find the time t equals the natural log of the ratio a over a naught divided by negative lambda. That is the working formula that we will use to find the time, all right? Or in this case, the age of the artifact that was mentioned in our problem. So, using this formula, the natural log of 20 over 160, okay, using your calculator, and then divide it by the negative lambda, or negative 3.83 raised to the negative 12 per second, that was earlier calculated here, we will arrive at this value, 5.43 raised to the 11 seconds. And then change this back to its equivalent in years, all right? We will get 5.82 raised to the third power year. In other words, the age of the artifact is approximately equal to 5,820 years. So if you notice, the age of the artifact is just a little higher, right? Just a little higher than the uh, half-life of cobalt, of carbon-14. Okay, the half-life of carbon-14, which is 5,730 years, is just a little bit below the actual age of the artifact, which is 5.82 or 5,820. So, uh, in other words, the process of carbon dating, determining the age of artifacts, these artifacts actually are remnants of living things, either from animals or from plants. Okay, in order for carbon 14 to be the result to be reliable, okay, we have to have an isotope like carbon 14 whose half-life is just a little bit lower than the expected age of the said artifact. We cannot use carbon 14 to determine the age of the Earth because, as we all know, uh, the Earth was created some 4.5 billion years ago. And using carbon-14 as our process, carbon dating as a process, okay, will of course not be a good idea, but instead there is another isotope that scientists use to determine the age of the Earth, and that is using the what they call uranium dating, because uranium, its what you call half-life is just a little lower, okay, than the expected age of the Earth. Question number 4. The isotope yttrium, whose mass number is 90 and atomic number 39, undergoes a beta minus decay, which actually is an electron particle, with a half-life of 64.0 hours. You measure an activity of 8.0 times 10 to the negative, 8.0 times 10 to the 16 becquerel. So this is the initial activity, or A naught. Question letter A. How many yttrium nuclei are present in the sample at the time you make this measurement? Question letter B. How many will be present after 12 days? Alright, so our first step in our solution is to find the decay constant lambda. So, again, lambda is equal to 0.693 divided by the half-life of this isotope yttrium. So, 0.693 will be divided by 2.30 raised to the 5th power second. Okay? And the result is a lambda equivalent to 3.01 times 10 to the negative 6 per second. The half-life has been converted to seconds from its original value of 64.0 hours. After which, we can now determine the number of nuclei at time 0, that is n naught. Alright, so we have our equation for the rate of activity, which is equal to lambda times n naught. And since we know what is lambda, we can determine n naught. Alright, we just divide. N naught is equal to the activity, 8.0 times 10 to the 16 becquerel, or per second, divided by the computed lambda in reciprocal second, that is 3.01 raised to the negative 6 per second. So second is cancelled. Our number of nuclei of yttrium, okay, therefore, at time 0 is equal to 2.7 times 10 to the 22 power nuclei of yttrium isotope. And then, for question letter B, how many will be present after 12 days? So we just use the formula to find the number of nuclei remaining after 12 days. Alright, so what we get here is, using the formula n is equal to n naught multiplied to Euler's number raised to the negative lambda t power. Substituting for n naught, the one we got earlier, 2.7 times 10 to the 22 nuclei multiplied by this number, 2.718 raised to negative 3.12. Okay, negative 3.12 is the result of multiplying the lambda, okay, and the time t. So what we got is a unitless number as the power for the Euler's number, negative 3.12. So using your calculator, you'll be able to find that the number of nuclei after 12 days will just be 1.2 times 10 to the 21 nuclei, or when expressed to the power of 22, so as we can see the comparison between n naught and n, that is 0.12 raised to the 22 power nuclei. So in other words, from 2.7 raised to the 22, okay, originally, that's the number of nuclei of yttrium, Then after 12 days, it has uh, decreased to 0.12 raised to the power 22 nuclei. The last question, number 5. Radioactive isotopes used in cancer therapy have a shelf life, just like pharmaceuticals used in chemotherapy. Just after it has been manufactured in a nuclear reactor, the activity of a sample of cobalt-60 is known to be 5,000 curie. When its activity falls below 3,500 curie, it is considered too weak a source to use in treatment. Supposing you work in the radiology department of a large hospital, one of these cobalt-60 sources in your inventory was manufactured on June 26, 2019. If it is now December 26, 2022, that's today, question is the source still usable? Given the half-life of cobalt-60, which is 5,271 years. Alright, so the solution to this problem is for us to determine the new activity after a given time has elapsed. The original activity in Curie is given 5,000 Curie. So what will be its new activity 3 years and 6 months after? Is it still above 3,500 Curie? Because when it is below that activity level, 3,500 Curie, we say that it is already not usable because it is already weak as a source to use in cancer treatment. So, our solution, we first convert, convert the given activity initial A naught from Curie 5,000 Curie to becquerel. We just multiply this 5,000 by 3.70 times 10 to the 10 becquerel, and we get the equivalent activity already expressed in becquerel, which is 1.85 raised to the 14 power becquerel. And then we also determine the time that has elapsed, okay, from June 26, 2019 to December 26, 2022, that's today. That is approximately equal to 3 years. And in 1 year, supposing we consider 1 year having 365 days, so multiplied by 3, that's the number of years that has passed. All right? And then the extra number of days from June to December, exactly from June 26 to December 26 of this year, that's exactly 179 days. So a total of 1,274 days has elapsed. When expressed in seconds, that's also equal to 1.1 raised to the 8th power second. So the half-life which is given in years is 5,271 years, or in seconds, that's also equal to 1.662 times 10 to the 11 years. I mean, second. So, we will find the decay constant, lambda, okay, in reciprocal second. So we just divide 0.693 by 1.662 times 10 to the 11 seconds, and we will get 4.17 times 10 to the negative 12 per second as the value for lambda. We will see the continuation of our solution in the next slide. Alright, so earlier we already got the value of the initial activity A naught, which in becquerel is equal to 1.85 times 10 to the 14 becquerel. So we can now determine the new activity A after that time elapsed T using this formula, A naught multiplied by Euler's number raised to the negative lambda T power. So substituting, all right, when you multiply, look at our power for Euler's number. Negative 4.17 times 10 to the negative 12 per second, that is the value for lambda, and multiply it by the time elapsed, which is 1.1 times 10 to the 8 seconds, and we will get this exponent, or the power of the Euler's number, negative 4.6 raised to the negative 4. This is a unitless number whose equivalent, okay, when calculated using your scientific calculator, will come out to be 0.9999 something, or rounded to 3 significant digits, is just exactly equal to 1. Multiplying that by the value of A naught, okay, and then converting the becquerel to Curie, we will get a value that is equal to 5,000 Curie. All right? So you will notice that the activity A after 3 years and 6 months, okay, has not practically changed at all. Our initial activity is 5,000 Curie. So the new activity is still 5,000 Curie. Therefore, our conclusion, the source is still very much usable. And this is to be expected because if you look at the value of the half-life of cobalt-60, right? Earlier, uh, we gave the value of the half-life of cobalt-60. It is 5,000 plus, all right, years. So for cobalt-60 to have a significant change in its activity or its ability, all right, to spontaneously transmute or decay is not significant. Okay, getting an activity that is not changed at all simply means that the number of days, or yes, the number of the time considered, okay, after the initial determination of the activity A naught, then 3 years and 6 months after, such activity, okay, has not changed significantly. It is almost the same as the initial activity, suggesting that, all right, the effectiveness of the source of the cobalt-60 substance is still usable as a treatment, okay, uh, for whatever illness, probably cancer, so as to come up with a significant change in the activity. Probably uh, the time that should elapse after the initial activity has been determined should at least be half of the half-life, isn't it? But since the half-life is so long, 5,000 plus years, okay, you cannot expect that the activity of the substance will really significantly change in just a very short period of time after. Okay, 3 and 6 months, 3 years and 6 months is such a short period of time to expect the activity of cobalt-60, okay, to really significantly reduce. So that's all for this particular video tutorial. Thank you very much for watching.